and my nick is showcoder. Hello, I am Jesus Olmos. I work in Fox IT NCCA group, and my nick is showcoder. I want to present a concept that is very useful for malware reversing. When we have the normal thing is we have the source code, and we compile this source code and we get the binary. But it would be nice to be able to obtain the original source and compile again the source. But during the compilation there is a loss of information and it's not possible to recover the original source perfectly. The compilers do some magic, but probably in the future with artificial intelligence we'll be able to generate a code that can be compiled again. But what is possible to do, and is not difficult, is to get the assembly code of the binary and modify a bit this assembly to compile again and use this code. So we have a malware, and we can extract part of the malware and we recompile this function, for example, a decryption function or whatever. This is a hashing function, but we want to know exactly which algorithm is. These are XMM instructions, and we want to extract this part of the malware and recompile to use it and generate, to see what is generating and if it's a CRC32 or what is. I did the ReAsm tool, which is a script that, for example, we have a Windows malware. With this tool, we can extract a function of the malware, of the Windows malware, and recompile it in Linux and execute in Linux in a controlled way. And it is using R2 pipe. This script generates 3 files. The assembly file, where there is the function modified to be perfectly compilable. A main to launch in a controlled way the function, and the make file. The main, mainly we have here the extern. This function is implemented in the assembly code, and we execute from C the function. So we have extracted a weird function from the malware that generates something, and we are executing in a Linux this algorithm and printing what is generating, for example, a bot ID or whatever. In the case of these XMM instructions, it was really a CRC32 on Dridex or Dridex. This is the assembly code generated by the script that modifies, for example, put labels to resolve the jumps and so on, and modify some instructions. If there is, depending on the implementation, for example, if we need a stack, we can allocate the space and set the ASP register and simply launch the algorithm. For example, there is a complex algorithm that decodes something or decrypts something. We extract this algorithm exactly, and we execute the algorithm with specific parameters or so. With different calling conventions, for example, in C++ calling convention, we allocate the Ds and set the ECX register and launch the function implemented in assembly. So we are executing the function of the malware with specific parameters and getting the result. Instead of implementing, in the case of base64, we can implement with one line of Python, but there are weird algorithmics, complex algorithmics, that this is just an example. This is an example. Then, depending the implementation, we have to compensate registers, or we have to put several instructions. This is the case of formbook. Formbook uses to use standard algorithms but modified. For example, the SHA-1 algorithm, the hashing algorithm, they modify something. It's not the standard algorithm. So instead of implementing all the algorithm in Python or another language, we extract the function. We extract in this case two functions and launch the functions here, the RC4 and big64. It's just an example. We are encrypting the communications, a text that is sent in the communications. Well, the script detects these branches and jumps and calls, and locates and put a label to jump to the label. And in this case, there are these labels. For example, if there is a branch, there is a label to jump with the address. And it is powered by R2 pipe. The good thing of Radar is that we can print the disassembly in a very similar format to the NASM. So we can recompile in NASM the code with minor modifications. Well, it is in the GitHub of Fox18. Some improvements. If we are extracting a function that has a call to another function, we could recursively extract it all the functions. Other thing is detecting the end of the functions to not specify the start and the end. This could be done with emulation also. So we can extract the binary blob and emulate it. But there are the initial codes, or well, I have found that there are a loop with a lot of iterations, for example, or there are anti-emulations. And in this case, we are executing in the same processor, so we are replicating the same state of the algorithm. There are some advantages to doing this way instead of emulation. Logically, we have to check that in the assembly code there are no centers or interrupts that could execute any malicious code. Normally, this is used for extracting algorithmics that is not using WinAPI or is not using dependencies. And that's it. Well, we have the ReAsm software and the malware. Here we have the base64. We can see the charset initialization, and this base64 has has some branches, loops, and so on. We launch the ReAsm. We select the malware, the name we want to choose, the start and the end of the function. And now we have the assembly code, the launcher, and the makefile. Here we have a perfectly compilable assembly code. And here we have the external. Okay. Well, I should put here also the parameters definition and so on, but it's unnecessary. It works in this way. And we print the result. Well, here we have so we can extract an algorithmic from the malware. In this case, it's a simple function, but could be another type of function that doesn't have external dependencies, like calling some APIs, and we can execute and replicate the same extract. Normally, in malware analysis, we like to implement in Python some features of the malware, like the emulation the protocols and so on. There are some things that could be done in this way, and other things no. So but that's it.
So sorry for the waiting. We are starting now with Ula. He will be showing the last updates on Frida. So welcome, Ula.
But the new feature in some of the new features in Frida 15 kind of started in this area, so we're going to show that. So we're going to go and grab the gadget, and I'm on Mac OS, so I'm going to go and grab the Mac OS gadget. I'm going to uncompress it and say I have some hello world binary here, such as this one. Where we have just a main function with an infinite loop, where we have a local variable n that starts at 1, and the infinite loop just increments n with each iteration and sleeps for a second. It passes n to a function f, and that one just prints it. Yeah, we can just run this program. So yeah, let's actually make a directory where we do our stuff. So we're going to copy the hello to here, rename it to hello C. We're going to compile it, and here we go. So now we can do dial B insert libraries, or if you're on Linux, this would be LD preload. So yeah, r2con Frida gadget. And as you'll see, it doesn't actually start, it doesn't enter main, so it's printing out, listening on yeah, localhost this port. And this means you can now do like now you can do like Frida ps-r or -h, and you can see there's one process and the name is gadget. It's always gadget. Then you can use like REPL or to Frida to actually attach to that process. And because we attached right away, it will resume. We can also do early instrumentation, but I won't dive into that right now. But that's if you want to apply instrumentation so that you'll see it if something happens very early. But yeah, we're in the process. So that's like the default way you'd use gadget. You can also configure it. So you can do like, you can add a config file, you name it exactly the same as a gadget, and you can do like interaction script, and actually we can go to the website and just whoops. Look at the documentation for the gadget, and so you can see it has a few. It has a few modes. So it's the default is listen. That's the one you just saw. You can also use script, and it can load a script for you and so on. So there's a new thing in Frida 15, which is instead of listening and like emulating a Frida server, you can do a connect. So this is this is kind of the opposite of the listen interaction. We can just show you the default config. By default, it will connect to localhost on this port. So we'll do that. Now let's go to the releases again and grab the portal. And the portal is the new thing in Frida 15. That means that you can have the gadget connect out instead of being connected to. So instead of being a server, it's a client. So you then run the portal that could run anywhere on the internet. Let's just move these to the r2con directory. So I'm going to make it executable, and we're going to run the portal. Now it's running, and if we do dial the insert libraries here, it'll start right away, so it doesn't stop like it did before. Add another terminal, another shell in parallel. We can do ps free ps dash this, just like before, and now you'll see that there's one process, and we can actually connect to it with a REPL. And here we go. So we're now inside this process, but we're talking to it through the portal. That means you can have the portal running somewhere on the internet, and and that way you can share it with others, and they can connect to it, and so you'd have like a remote code execution as a service. That is quite dangerous, obviously, so be careful with this. That's why now in Frida 15 there's also support for TLS and authentication. And also, because of the flaky nature of networks, there's also an offline support now. So like if the client gets disconnected, it can keep scripts loaded up to a certain time that you specify, and messages will just be buffered at that point, and you can reconnect and get the messages that were emitted by any scripts in the meantime. And if you don't reconnect, it will unload the scripts eventually. So that's basically the portal, but it has a lot more things under the hood, but I think we won't have time to go into those now, but basically I'll just cover it briefly. That so this portal also has allows the clients that talk to it to send it messages. But the default portal that we have running here doesn't do anything with those messages. So you'll have to instantiate it through the API, and then you can handle those messages. And that means you can implement chat protocols or other things. So you can make like collaborative apps on top of this. But another big change now in Frida 15 is that there's also support for. I will actually change the protocol to be WebSocket based. So that means you can have a web app that talks to a Frida portal or a Frida server without any middleware. You don't have to write any middleware unless you want to, of course. And that means it's very handy for prototyping purposes. So say now that we want to start a web app. Let's just call it web, and yeah, we'll use single page app framework or Quasar. So create the client. This is based on Vue. Yeah, so this is our web client. Frida web client. Frida web client example. I'll leave the defaults. And here we go. This will set up a skeleton for a web app, single page web app. And once that is done, we will we'll just tweak it a little bit. So this has the some boilerplate that you'd have in any front end web front end app or typical front end app. So here we're using the Quasar UI toolkit or framework, and this uses Webpack under the hood. I don't have time to go into all the details on that, but we have to install some more dependencies. So there is a library called Node debus next. So I've tweaked that to support running in the browser. So we'll just npm install that, because Frida uses WebSockets now, and the protocol there is dbus like before. So there is a library for us communicating over dbus, so we can just install that. We'll also need a few other things, dependencies for running in the browser. I'll make this a bit more streamlined in the future. So we'll install those. And then we'll have to hook them up to the build system. So here we go. So we'll add two more imported packages here, and then Webpack will customize the build configuration for the Webpack build configuration, and I have some pre-baked code here. Basically just using a dummy shim for the modules that we don't actually need. This is a bit dirty, this will be cleaned up later. And telling it that when it uses a Node.js process module, actually use process/browser and so on. There we go. So we need a source shims. Source shims. I'm gonna add a dummy JS here, and then yeah, we're just going to ReAsm set up some scripts here, and we want to have a couple that will run a development server on localhost and target for building, which we won't use for this point, but that's like for production build. So we'll do npm run dev now, and that will actually build this from a single page app. And here we go. So this is just a boilerplate Quasar app where you have some to-do items, and if you click on them, this counter down here will increment, as you can see. So yeah, now let's start to fill in some code here. So I'm gonna hop into r2con web client code, and here we're going to look at the skeleton of this app. So you have an app view at the root, and you have some components, and the one with the main content is called composition component here. And this is the HTML that gets rendered, as you might recognize it. The title, and then a list of to-dos. So v4 to do into do's, then it repeats this fragment here. And here is some code, boilerplate, and so I'll start here. It defines the component, some property, title, to do's, meta, active, and in setup it will populate, return the things to initialize with. And here now we're going to let's see, to actually add some code that will connect to the Frida server. So let me just peek my cheat sheet. Yeah, we're gonna need some extra imports. So I'm gonna include these to here. So the dbus next one, we're also gonna add the I think I was muted in the beginning, sorry. Let me see if there's any questions that I missed or so that's good. I'll keep an eye on the chat if you have any questions. Right. So in the meantime, yeah. Next up here, let's see. Yeah. So we added a couple of imports. We want dbus next and duplexify. I'm gonna gloss over a lot of details here, but this will be easier in the future because we'll probably have like a package for that just hides these details. But here you'll see just the raw what you need to do without that. Yeah. So we need a helper function to turn a WebSocket into a Node.js stream. I have that already baked down here. Just pasted that in, and now let's get to the interesting part. Say we want to run some code when this component is mounted. Just gonna prototype that here. We're gonna wrap the event stream, new WebSocket, localhost. This is where the portal is running. And we're gonna finish this block here. Just something goes wrong. Whoops. Yeah. Okay. So we have now we have a stream for the WebSocket, and we're going to do create a peer bus. You're now using Node dbus over this WebSocket, so a peer-to-peer dbus. We'll set auth methods to empty because there's no authentication at the dbus level. That's at the Frida protocol level. And now let's also get a host session object. Basically in the Frida protocol, I'll show you quickly where that is. Lib base session vala. There's the host session interface, and this is the one that has enumerate processes, enumerate applications, attach, and so on. Things that might be familiar to you if you have used the Frida APIs. Right, so we're going to get the host session object. Yeah, we'll do get bus get proxy object, and Frida host session 15, as you can see in the code we just looked at. Frida host session. This will actually get all the method definitions and so on over the WebSocket. These could also be provided at compile or like here through the to save time to save that round trip, but we're not doing that, so we're doing it dynamically. It's generating this JavaScript wrapper for this class dynamically. So now let's get the host session object. So to get interface on that, the one we got, it's named exactly the same. And here we go. So now we should be able to do like await host session enumerate processes. Yeah, we'll need to define this. I guess actually we'll just need to define some types to help us here. Because the enumerate processes, if you look at the API definition here, it turns host process info, and that's a struct, and those are represented as lists in JavaScript. So it's a PID, is the name and the parameters. So here we'll just define that, and we'll say it's PID string. That's wrong, actually. It should be a number. Name string, and the parameters. Host process parameters or something like that, or just process parameters. We won't actually define what those are at this point. What am I doing? Yeah, that's host process info, PID, number, name, string, parameters, process parameters, and actually I'm not sure which TypeScript compiler version this is, so maybe I should just do this. No, okay, no. I've messed up the declaration here. This is a type. We're defining a tuple here. It has the PID, the name, and the parameters. And the process parameters, we won't go into those. Yeah, so we'll have a list of processes, and for now we can just do console log processes, got processes, and processes here. Okay. Yeah, let's see if we can actually build this. There's probably some mistakes. Transform callback. Yeah. Probably missing something up here. Yes. We need to import those. A few things from the stream package. All right. Let's go to the terminal. No issues found. Okay, so maybe this is good. Okay, let's go here. Open the inspector, and yeah, got processes array of 3. Well, 1 element with, and that's our process. So there's just one process here. But if we were to run like a Frida server, on the other hand, instead of a portal, and reload, you'll see a lot more processes. So here you can see all the processes on my machine. Yeah, so I think that's pretty much all we have time for. Yeah, okay, we have 3 minutes still. So yeah, we got the list of processes. Could just iterate over it yeah, where's the tuple? So pit name parameters. Okay. Here we go. Now the next thing would be to actually populate the UI here and make this an interesting app. Yeah, that's left as an exercise to the reader here. Other than this, there's also, this means that web browsers can talk directly to a Frida server now, and or a Frida portal, because a Frida portal has 2 interfaces. It has the cluster interface, which like the gadget connects to, things that form a cluster of all the processes that you can instrument. And it has a control interface, which is the part that emulates a Frida server, and that's the one we're talking to from the browser here. And what's cool is that you can also set up a peer-to-peer connection. So if, like here, if looking at the terminal, say this portal was running in the US and I'm in Norway, but this process that is in the portal is in Italy, say, then we don't want all the traffic to go to the US and then to Italy. We would rather just talk directly to Italy from here to save that the cross-Atlantic round trip. So there is now peer-to-peer support, and that's compatible with WebRTC. So we could actually use that too in this web app and be able to talk directly to this process here that could be in another country. And the portal could be in a data center on another continent, and we wouldn't have to pay the price and delay for that and the bandwidth costs if it was, like, say, AWS. So that's also new. And another thing that's pretty cool is that we have a portal running here. Now if I reload here, there's no processes. But you can do Frida join, so say Telegram is the name of a process on my local system. Well, actually, Frida join. I'll show you the help text. So the target process, the portal location, the portal certificate if you want to use TLS, and the portal token if you want to use authentication. So say we do Frida join Telegram, but we can also use -u and use a process name for a process running on my iPhone, for example, or an Android device, or a process on another system on a free server. And the portal is, in this case, on localhost. So I'll just authenticate, and here it's joined. And now if we go and check the process list, you'll see actually that there's a Telegram process here. So now this, so it means you can use, I mean, you don't have to use the gadget. You can also use Frida in embedded mode, injected mode, and be able to join processes. So you can take a process that's running on your phone and have it join a portal that's in another country, and that way you can share access to a process with someone and provide remote code execution as a service. Yeah, other things, there's also system parameters available now. So if you do, say you have a Frida device, you can do enumerate system parameters, query system parameters, if I can remember correctly. Yeah, that's the one. Yeah, so the architecture of the system and some details. So there's also process and application parameters. So when you do enumerate processes, you can do scope. So you see here the parameters is new, but it's empty. But you can do scope equals metadata, for example, and you get a bunch of more details about each process, the user it's running as, and so on. And there's also a full scope to get the icons if available. So yeah, that's pretty much it. If you have any questions, feel free to drop by the Frida channel on Telegram, or well, I'll also be following, of course, the r2con channel. So yeah, thanks for watching.
Thanks, Ola. We'll go into the waiting scene, and where next talk will be from Lars.
Good evening, ladies and gentle people. I hope you're all doing well and the stream is switched over. As you can see, I'm still in my apartment here in Oslo. Hopefully we can meet up soon. I'd like to have a chat with some of you guys. Anyway, welcome to my talk, Flipping Malware with flip.re. I'm going to let me just see. Okay, we are live. Good. Perfect. So it's not just like a delay between me and Pancake, so it's kind of nice. Make sure that everything works. So I trust you all enjoyed Ole's talk as well. This talk also will touch a little bit on Frida, how we use it in our system, and R2, of course, lots of R2 stuff. So I'm going to talk a little bit about how we are designing an interactive malware analysis system. Bring up my presentation. Oh yeah. So you can see I put this question link on top. So if you have any questions for me, then just go to this link and type your question, whatever it is, and I'll try to answer some of them towards the end of the talk. I won't be looking at it during the talk, but I'll have a look after. So yes, perfect. Let's go. We are an early phase startup based in Oslo and Warsaw. Technically, today we're called OX Epic, and that's likely to change though. We've been using this flip.re name for a long time now. I did a talk at r2con last year, so if you are watching this in a recording, you can go and have a look at that as well. I'm not covering the same thing today, but some of the stuff we touch on will be based on it. So the team right now, the core team is 2 people. We've been doing this since basically the start of the pandemic. So we've been quite good at working remotely. So if you do want to work with us at some point, then it's no problem if you're remote. We have basically our background is former sandbox developers from the anti-malware or the antivirus industry. We used to work for what was originally a Norwegian antivirus company called Norman back in the days. And our vision is basically to empower your security team to reverse engineer malware blazingly fast. So that's us. So when I analyze malware, I don't do it on a daily basis anymore, but I used to do it like 10 years or so. Since then, I've been mostly developing technology and tools in order to help people do it, and also automate that in like a sandbox. But for me, analyzing malware has always been about trying to combine the powers of dynamic and static analysis. So dynamic analysis is anything that looks at the behavior, such as, for instance, Frida, that Ole probably covered in the talk before this. Way back when, we mostly used debuggers, so things like oleavr and what have you, and others, soft dice maybe, those things, which is kind of like a nice way to locate the interesting code. That's basically the idea of it. So today, a lot of teams and malware analysts also rely on sandboxes quite heavily, since they are really efficient at, or they will give you some answer in some cases quite fast. But it's basically an automation of some type of behavior-based monitoring. But they are inaccurate. So if you want to get into the details of what's going on, or you fall in the sandbox, you don't produce much result, you need to dive in and do like a deeper static code analysis, or you look at the like assembly code and you do, reverse engineering. But this is slow, and knowing that there are about I think last year I mentioned there was like 350,000 new threats every day or something, according to like an antivirus testing organization. So there's no way you get close to analyzing that many statically. Now the challenge today is basically the attacks are becoming more targeted and more advanced. So for these threats, you should likely expect them not to run in a sandbox. And as a result of this, you should also expect them to be undetected for a long time. Because you have to remember that the people who are designing detection technology also rely on typically sandboxes. So if you can't analyze a sample, then it's also hard to detect it, basically. Because you cannot really assume that something is bad unless you know it's doing something evil. Or and the more advanced threats, like typically what we call evasive malware, also actively try to make analysis challenging. So this is basically the task you're up against. Now, if I remember back to when I used to do this on a daily basis, this was basically my workflow for the most part. I would use something like a debugger, get some type of file, and then assuming you can mostly assume that it's packed in some way. So just looking at it in, I was using IDA at the time, but even you can use R2, IDA, Hopper, Binary Ninja, whatever you use. You need to kind of locate the code that you want to look at first. So I was doing that using debuggers to like unpack it, and then you dump the memory somehow once you've revealed the code within it. I'm assuming it's not like something like a VM based obfuscator, but something that actually unpacks itself in memory. But still, it's kind of messy because you need to like dump the file somehow, and then in order to import it into some analysis tool, you typically need to like fix like imports or something that makes the static analysis tool parse the APIs, for instance, so it's easier to actually look at the code and understand what happens. Today, you can also use sandboxes for this instead of a debugger. But regardless, if you throw a file into a sandbox and you get lots of memory files back, it's still kind of it takes a long time to perform this type of analysis. So that's what we're trying to fix, essentially. So let's talk a little bit about the system, how it's designed. The number one component of any like sandbox and malware analysis platform is isolation in some way. The idea being that you don't want malware to run on your system or do evil. I mean, so you need some type of isolation. For the most part, you will use like a Windows VM for this, or like assuming you're analyzing Windows malware, you would need like a virtual machine. In our case, it runs under QEMU, which is also using KVM as an accelerator. I have a lot of good experience in using QEMU in the past. And if you remember back to my talk a year ago, I also talked a little bit about how we modified some of it. So in one way, you can say that we have two layers of isolation, but really the main isolation in terms of preventing the malware from doing harm is the VM. So the second thing is that we've designed the entire system using Docker containers, just for mostly for convenience though. What I'm just mentioning here, it is kind of like an isolation as well. But mostly this is because we try to keep things like separate and clean for ourselves. So number one, we want this backend to be able to run mostly everywhere, even in the cloud. So it's and using Docker kind of forces you to have like a nice API design and all that. It's been quite good. But still, even if it's isolated, you need to interact with it somehow. So the way we do this is basically we interact directly with the Windows VM via Windows Remote Management, and then we use libvirt currently to control the like the logistics of the VM, starting and stopping it, and creating snapshots and all that stuff. And we're interacting with QEMU via a modified GDB. This is the thing I talked about to some length last year, which is basically just for us to be able to instrument the VM so we can control and single-step things that run inside the VM from the outside. And yeah, we call this service a construct currently from the Matrix, where like you remember this loading screen in Matrix where they could load all sorts of things like weapons and training simulations and all those things. So that's where it's from. So the second component that goes into any type of sandbox or malware analysis type of system would be some type of monitoring component. These can be placed in many places. Like you could have monitoring in user mode, you can have some monitoring in like a kernel mode, say you write some driver, or you could have modules operating on the hypervisor level, more like. So it's, in a way, this is a little bit oversimplified, but in a way it's running under the kernel. But it's comparable to placing something inside the kernel or the VM is comparable kind of to you doing it in the hypervisor. But I guess it's a little bit more stealthy. And if you're afraid of the malware actually detecting the presence of your monitoring component, then you want basically to place as little inside the VM as possible. But basically what we're doing now is to use Frida to generate events. So inside the VM, we run Frida server, which is nice because it gives us a lot of flexibility. And regarding, even though we have plans of adding components that run in hypervisor later, I think it's still extremely nice to have an agent in user mode, simply because there are lots of interesting things happening in user mode that you typically want to intercept and have a look at. This service we call Nexus. It's using the Rocket RS, which is a Rust framework, Rust web framework, which has been really nice to us so far. I kind of stopped using C as my primary programming language like 2 years ago. I'm more or less switched to Rust now, and I like it more and more. So yeah, and we still, though, what's nice about Rust is that you can still interact with C libraries. So we're able to basically just work directly with the Frida core SDK, and then basically the Frida core SDK will be the client communicating with the server running inside the Windows VM, and then we just forward the network traffic to it. And the last component will be R2, which we also use from Nexus via the and then using the Hyperflip IO plugin that I discussed last year, which is utilizing R2's way of abstracting away IO, essentially. So we're using the debugger interface, you can say, in R2. So we send R2 commands, we have some our own commands, and then Hyperflip basically implements the underlying technology that a normal debugger would use. This Hyperflip talks to QEMU via a modified GDB. This is just to send some extra registers over, and then some minor things. And it also shares the physical memory of the Windows VM with QEMU. So QEMU can share the backing memory of the VM out of the box, actually. So combining those three access, Hyperflip does all of the heavy lifting in terms of converting a virtual address to a physical address, and then all of that stuff. Yes, very good. So Frida, we also use Frida to load programs inside the Windows VM. You need, however, you need some way of starting programs whenever you, so we use Frida for that. And using it, we can basically hook any user mode function. Which is like extremely flexible. This enables us to basically keep like a default script. At least that's what we're doing now in the first version. And then we can still expose this to an analyst. Like you need more details about a specific set of APIs, something like that. You can do your own custom scripts, for instance. And also you can avoid hooking functions if they cause problems. Like say the malware is trying to check for the presence of hooks, for instance. You can remove them, and it just gives you a lot of flexibility. And so we use this as event generation. So basically Frida has its own message loop, and whenever a function that it hooks is called, we can basically output events from that. So I mentioned Hyperflip. It basic, remember Soft Eyes or something like that, which is kind of like a stealthy debugger that works underneath the Windows kernel in a way. So that's kind of like the idea of it. It's supposed to work without Windows knowing we're there. So that's basically the gist of it. It means we can debug any code running inside the VM from the outside. It gives us full access to inspect all of the virtual address space, all processes and kernel mode, and it's yeah, it gives us sort of some superpowers. Anyway, see my talk from last year if you want to have some more details about it. Since last year, we've added some new cool features to it. Basically, we added support for multiple CPUs, which is one of those things where I didn't really want to do it in the initial version because it's a little bit of a hassle. But we kind of decided to do it because it's one of those things that I think could be hard to add later on. Once you start making lots of features on top of it, it can be kind of hard to go back and like expand it from a single CPU type of thing into a multi-CPU. Talking from experience, maybe maybe I've done this in the past somewhere. And also, if someone remembers 2 or 3 years ago, I don't know, we had this R2 table at CCC, and I was doing trying to get something similar in like a related project I did before this. I was struggling with QEMUs and how memory translation worked, and I kind of figure out why it was a problem eventually, which is related to something called the PCI hole, which I can talk about the details. Anyway, we lifted the kind of the memory limit we used to have, which was somewhere between 2 and 3 gigabytes, and now we can basically work with as much RAM as we want to give Windows, which is nice because it means you can have a better experience inside a Windows VM. So I want to mention give a big thanks to Defragger, who's been helping us a lot with testing on his as a special QA system. He had a physical desktop that was just so different to my system, and also so he triggered like all of the edge case bugs. It's nice to get those fixed. So thanks a lot to Defragger for helping out. Okay, so I'm just going to mention some of the special commands so that when I show you in a demo soon, you can know kind of what they mean and stuff. So any IO plugin in R2 can implement its own commands. This is kind of like a little funny. We used to patch R2 a little bit. We still patch R2, but not in the same way. So one day I was I kind of woke up to it didn't build anymore, or it didn't work. That was how it was. And I was getting so used to using that, and also I used it in the automation stuff from Nexus. So basically means that with the commands we issued had backslashes in them, and when I guess this is kind of optimistic from us, but we were just like building from. Look at this like the details of this commit. You can see in detail what he changed. Is apparently I didn't know that it was deprecated, but apparently it was. According to the documentation in the source code, you can see that the backslash command is no longer available to use, but instead you need to use the equals bang or the colon. So I kind of like it to be short and nice, so I kind of prefer the colon thing, which is funny because then all of our commands become more interesting. So these are some of the the hook and flip commands we use. We have some very basic analysis features today. We basically analyze PE headers in memory just to get some data on things like the entry point of a module. That's EA. We added hardware breakpoints. You can do a DRX thing, mostly because we needed a little bit different implementation than what is normally in R2. You can use DRXE for entry point. You have the CPU command. I might change that to just be the C, because it looks like a funny little place. And then you can switch between kernel and user mode to some of the other commands. So if you list modules in kernel mode, you would list the kernel drivers, but if you list it in user mode, you would list the loaded DLLs of its current target. And then you can display a live process and target, but the most funny one is the detached thing, which I kind of I used to be a small cap D, but we now also support this super smiley thing. So you can see me type the smiley. It means that I'm detaching from the VM. Okay, so our system basically want to combine these things. So Frida, R2, Hyperflip, VMs, and but we need something else, like something to, because like something that users will interact with, which is of course a UI. And I realized that R2 might not be like the most intuitive thing to learn, so I hijacked this XKCD thing and sort of just gave it a, you know, easy IDA binary ninja and hopper, and R2 has like a different type of curve where people are dying on their way up trying to learn this. So I know that intuitively it's not necessarily like using R2 might not be in some aspect like the best route in order to ensure like you have like a nice user experience in the end product. But I really like R2 because of its like its speed and its flexibility and the fact that it's open source. You can change things. So I think our approach is basically to build some type of analysis UI on top of it. I know R2 already has like multiple web UIs, but I think we might actually end up making another one. So if you're right there and you're interested in doing these things, absolutely reach out to us, because neither of us are experienced web developers, so we might need some help going forward. I want to say we did do some considerations on like the technology for different UI things. I think my main takeaway from it is that web technology in general has become really like nice and shiny. So I myself, actually, I've been through using various editors in the past, like I switched from Vim to Emacs, and then now I'm actually on Visual Studio, or I'm using the code package in Linux, which I really like, which is based on Electron. So that's again also web technology, you know, basically HTML and CSS, and there are lots of like nice JavaScript libraries for things. So, but also the fact that we want our system to be able to run anywhere, potentially also in the cloud. So to make it easier for people not having to run everything on their system. I think for us using basically accessing accessing it from a browser could make a lot of sense. So, but again, we're not experts at UI development, so we might need to reach out to someone to help us improve this. But we call the UI component, or it is also its own Docker service we call FrontFlip, which is based on Next.js, which is a framework built on top of Node, basically. So it's the UI is basically made in React. So I want to give a big thanks to Jerry, my friend, for helping us out, kind of like deciding, basically making like the initial version of this, and just basically giving us some advice on how to proceed in the world of web development, which we knew very little about. So I want to mention a few kind of interesting libraries. So if you're doing something similar in your own kind of occupation, or there's a couple of libraries that we're using today that I found very helpful. One is the NoVNC JavaScript library. If you go online, there's something called a NoVNC client, which is a way to access, in our case, a Windows VM from your browser, essentially. Which is more like an application, but also they have like a smaller JavaScript library that the application makes use of, and that thing we are now using, and it works very well with the QEmu's WebSocket VNC, and it's been a really nice experience. I think it's kind of cool to just pull in this library, and then you can connect to QEmu and you control your VMs. So I think that might be something that could be useful if you're doing something similar yourself. The other cool thing that I managed to find, I wanted to kind of expose lots of features really fast. And regardless, I really like the R2 terminal. So for myself, I want to use the terminal, not necessarily whatever we might end up making in the long run. So we're using something called xterm.js to bring R2 terminals basically into the browser. So there's two components involved in this. One is xterm.js, which is the JavaScript kind of library to basically the visual part of it, I suppose. And then there's node.pty, which is a way to fork pseudo terminals. So those two things work together. So node.pty would run on like the server side, and then the xterm thing runs on the client. These are both maintained by Microsoft and actually used in Visual Studio. So and lots of other products that use like terminals. So absolutely check those out if you're doing some cool. If you want to do some cool terminal stuff in the browser. And then finally, we just actually this week implemented streaming of Frida events, so that you can sort of see the events as they come in the UI. For this, we actually used something called Socket.io, which is like a thin layer on top of WebSockets. So cool. Okay, let's show you the world of Flip in a cool live demo. Aha! Welcome to our world. This is Flip dashboard. Behind the scenes. This is a dashboard. Basically, the idea of this is that you drop a Windows ISO into the system somehow. Right now, we're just adding it from a disk, but the idea is that we automate the process of just dropping a Windows ISO into it. You can sort of just parse it. We select whatever version you want, enter your product key and those things. You can choose like a CPU type. These are the ones that are supported by libvirt essentially. Give it a name and whatnot, and it will just automatically install. And then it should basically create what we call a base image. This base image is then the what we base virtual machines upon. So it just means that if you want to make multiple virtual machines, they can all share the same base image, so that you don't need to install from the same ISO over and over again. From base images, you can create virtual machines. So you can see I have created two. One is called Flip and one is called Flop. And when you create the VMs, you can basically select how many CPUs you want it to have, type of, how much RAM you want to give it, depending on how much RAM you have available on the system. So right now, as I said, we kind of support infinite RAM, but it's lying a little bit. So I think there might be some upper limits on like 16 gigs and something in this version, which is again due to QEMU actually. So furthermore, the idea is that you spin up a VM and then you create some type of snapshot from it. So this becomes the starting point of your analysis. And when we do this automatically, we also automatically install Frida server on the VM, so that's already there running. Finally, when someone gives you a file that you have some reason to assume is malicious, or you find it suspicious, I suppose, the idea is that you just go here and you drop it. You select the snapshot. You can see my great UI skills. You can see clearly it's a camera. It's like taking a snapshot. And then we just hit analyze. And then from here, basically, what it will do is would start with reverting to a snapshot that you already made. So you start out in some clean state, presumably, where Frida server is running. and then it will basically use WinRM to transfer the file into the VM. And then you can see Frida is loading, attaching to it, loading our default script, and running the program. And finally, we just report that it's running. And also you can see that the entry point has been reached, because during these initial steps, we do some extra parsing and make sure that the entry point is actually been executed. This is useful if you have a corrupted file or some file that is missing a DLL, for instance. That typically something, if you run it in a sandbox, sometimes you will just see that it doesn't start and it doesn't give you any events or anything, so you don't really know what's going on. That's why we added that extra kind of logic of parsing and making sure that the entry point is actually hit. And one more reason that I will come to in a second. So you can see here, this is the VNC panel using the NoVNC JavaScript library that I mentioned. In here you can see our very, very friendly software, which is a fun demo that my colleague Carol made, telling us that it's he knows it's in a virtual environment. So this is kind of like the idea of lots of malware, if, you know, especially maybe the more I wouldn't say, yeah, more targeted ones, because it's quite common these days to try to detect like a virtual machine or something else that, you know, prevents them from running and prevents them from being analyzed. Yes. So here you can also see some events that Frida has submitted. You can see some create file events which just have been hit, and a call to something called get computer name exa. So some of these things could be, I mean, could give you an indication of what to look for if you were to kind of get around this thing. And I mean, obviously, if you're analyzing some type of malware that doesn't want to run in a sandbox, your first step is to make it run, essentially. And thus revealing whatever hidden code or things it might download from the internet, or, you know, things like that, things that you want to analyze statically, essentially. So I'll get back to this get computer name in a second. I want to show you the R2 terminal. So right now we have one for memory and one for file. The memory one isn't connected yet. You need to click this intuitive connection symbol. But the file is basically just an R2 terminal where we just open the file in R2. It's as easy as that. Because sometimes you just want to have the look at the file as you're running things, and it's easier to just have all of the analysis been done for you on the file itself instead of doing it on the entire memory space of the entire VM. And also there are some analysis features that currently don't work in the memory thing. But get back to us in a second. This is how it looks. It's you can do a full screen thing. So kind of like this, having R2 run in the browser. Excellent. Yes. So in this case, if you wanted to, let's say you found it a little bit suspicious that it would call something like a get computer name. If you are over this, you can actually see a description of what get computer name actually does, and it says that it retrieves a NetBIOS or DNS name associated with the local computer. The names are established at system startup when the system reads from the registry. And so this is a way to get some information about the system. So let's assume that this could mean that maybe it's looking for a type of system it wants to prevent being run in. So what we can do is to run this again, but this time specify that instead of running it to completion of however long it wants to run, we can tell it to break on the entry point. Well, as I said, we do some some logic when it loads up in order to basically determine if an entry point is reached, and we're also able to place breakpoints on the entry point essentially, and then we load it with Frida, and if the entry point is reached, then the entire VM will be frozen in time and space, and the CPU will basically be executing the first instruction of the program. So this is a kind of like a nice way to get you to the start of an analysis session. So run it again. We'll spend some time in reverting the snapshot. Transfer the file over, load the file, attach to it, and then it says that the entry point has been reached. And the load state is no longer running as it used to be, but it's now loaded. And if you, I will probably add some type of ice cube symbol or something that indicates that this is frozen. But if you move the mouse over it, you can't really, it's basically frozen in time and space. And from here, we can now, in addition to the file terminal, which is the same as last time, we also already brought up the memory terminal. And this is where we execute, we basically run R2 with the Hyperflip plugin. So you can see the command here actually just tells it which process that it should use as a target. Some extra parameters, don't worry about it for now, and then you can see this the flip URL basically it will be used for Hyperflip. So it will tell you that it has connected to the share memory file, which is the physical memory of the VM, and it also has a connection to GDB, which is how it retrieves information on registers, for instance. And it will print like the live processes that runs on each of the CPUs. So look, yeah, if you remember, this VM has 4 CPUs, so you can see that they all run different threads. Some of them, this is the idle thread, for instance. Anyway, this address means basically where you dig into. So you can see here that we're now the instruction pointer is now at the entry point of the program that we loaded. Obviously, the base address here is different. Well, you can see the base address is loaded at 14 hex, but it ends with 1438, and the same thing here ends with 1438. So the first part of it would be the base address. So you can get using, like, you list all the modules with DMM as which is a normal R2 command. If my OBS you can grep for demo. You can see this is the base address of it. Okay, so now if this is basically the start of our analysis. So what I want to do now is to have a look at the file on disk, try to determine. So assuming that we think this get computer name EX is suspicious, I want to determine where it's run from. If OBS will let me do that. Okay. So in R2 we can run some analysis, and we can assume that it imports. So II lists all the imports. You can use this dot command to bring up the HUD, and you can search for the get computer name function. Seek to where it's called, or seek to its address basically, and then use like an xref from here to find out where it's called from. We can see that it's just one xref, so it's just called from one place in the code, which takes us here. You can see, hopefully you can see this. There's a call to get computer name. Following that, it's basically testing checking the return code, which is this is a Windows API. So it means that 0 is error. So jump not equal means that on success it will jump here. And then you can clearly see that it's moving some string bank.com, and then after that you can see a call to what is string compare. This is Windows version multi-byte string compare thing, and then after that it's basically checking that return code. So this means that it's basically using the output of get computer name, which basically gets the domain of it. It's now making sure that it's the name, the domain of this machine it runs on is the domain it wants to target, essentially. So in this case, it's kind of like an illustration. If you write a targeted malware that only wants to run on a machine where the domain name is bank.com, then if that domain name is something different, then it won't run in your analysis system without the sandbox or otherwise, which is hard to fake. I mean, it's hard to get, it's hard to write or to create a sandbox that runs or every, you know, type of all malware, even though you're regarding whatever they check for. What we can do is basically to go to this address ourselves in our debugger, which is basically here. So let's just note the address of it, which this thing happens. See the call to string compare, and then there's a test instruction, and then the branch. So if we go back to our debugger, and then we place a breakpoint here, and then we can sort of take the other branch, like basically force it to take the other branch, right? So we seek to just use the base address. Yeah, so the test instruction is on 10F5. We can see that if we disassemble this as well, you can see like the similar assembly. It's different because some of the analysis information is missing, right? This is also the challenge if you analyze a raw memory dump or something where you don't have additional meta information. It's hard to understand what's going on. So our goal is obviously to improve the analysis so that we also do all the analysis directly in memory. So, but basically what we can do is to place a breakpoint here on F5. You can see this B here means that the breakpoint has been placed. And then we can just debug continue it. And then this one will unfreeze for a second. And hit that instruction, F5. And now from here, remember that we just removed the breakpoint. So it's testing EAX. If we go to this debug mode, you can see EAX, which is a part of like the lower part of RAX, which is FFF -1. So assuming it's calling string compare, string compare returns 0 if they are equal. So if you assume that it wants to run on a machine that has bank.com, you would assume that the output of string compare would be 0. So we can fake that just by basically using dr to list the registers, and then we set the value of RX to 0 like this. You see again now RX is 0, which means that whatever branch it took based on this it will now take the other branch. And from here we just let it go again. We will continue it. Ooh, and it's running. And you can see things happen. And you can see this. My colleague Carol trying to be very funny. But it's not necessarily a very friendly software. So the idea of this is basically you have some type of malware that don't run properly, and you, by combining static analysis and dynamic analysis together, you can sort of first of all force it to run by just manipulating it, and also secondly you can potentially just perform all of your analysis inside one system instead of having to export it and import it again as well, which hopefully will save you a lot of time. Good. And if my OBS is happy, I can try to go back to my slide. Very good. Let's see. I'll share some. So you can see the link. And I just wanted to share. I see I'm getting closer to my time limit, so I'll open up for questions soon. I just wanted to share with you some of my challenges preparing for the conference, and I was doing we were doing like a large refactoring of everything, and a few weeks back, well, first of all I should say that I had a lot of struggles for a long time with this laptop. Mysterious things were like crashing when it shouldn't, and I've been pulling my hair out trying to like understand what's going on, and there's been like lots of cases where things have like just seg faulted left and right, and things in Windows with blue screen for no reason. And I'll obviously think it's my fault. And then I go into the editor, try to fix things, and then my editor would crash. And it's like, yeah. So I've been also trolling the Arch Linux forums, trying to look for anyone else that would have like a similar problem to me, and no one had it. And then 2 weeks ago, I ran this memtest program, which is like one of those things you boot from a USB and you run it. It found like 1,586 errors in my RAM. So apparently my RAM has been broken for the past few years, causing a lot of headache. But I think with that, I had some extra slides on basically how we do the reach the entry point and some of those kung fu things. But I think I would just have a look if there's some. I don't see any questions. Yes, if there's no question, I might continue. Unless I screwed up somehow. Yeah, I don't see any questions, pancake. There's also lots of lag, so it's kind of. Okay. Perfect. That's I'll just say this thing before it's over. So if you're working on something or find this interesting, feel free to reach out to us. We're still in an early phase where we're developing basically an MVP and a minimum viable product. But we will very soon be looking for especially security teams that might be interested in like trying out and helping us developing it, and also smart people to join our team. We definitely need help on the UI if you're into Rust programming or those things, or if you're into reverse engineering in general. We also need more people going forward. So feel free to reach out to me. and I hope to see you guys very soon. I plan to be at CCC if it happens. So if you're at CCC, come find me. And if not, hopefully I'll see you at r2con physically, like next year. Thank you all for watching, and enjoy. I think there's the R2 Wars coming up, and then after that, I believe Pancake will do a presentation. Or the other way around. Anyway.
Thank you, Lars.
And I see you soon.
So it was a nice presentation. So thanks for presenting in r2con. Now we have some music, and then we will switch to the R2 Wars competition. We'll be running in a few minutes. So, welcome to the second round of Earth Wars. We're running now with 8 bots. This is gonna be taking a little bit more time, but at least we have some better understanding of how the bots are competing and how the game works. So you can see in the left side there is the blue color, and there is the green and red colors. That means that when the blue bot is reading, it will be painting the block in green, and when it's writing, it's painting it in red. Same goes for the other bot, which is the red one that uses yellow and orange. You can see the code of the assembly that is getting executed on every instruction on each side. And as we explained at the beginning of the conference, you will notice that it's not executing every instruction every time. We're executing using depending on the cycles that this instruction takes. So instructions messing with memory are slower than instructions messing with resistors. And that's another rule for playing the game. You need to be careful about which instructions you're going to use and how to fight with them. Now we have in the first position Ricardo APL, and second one Zeta. Then after this Amphibia, who basically rides one position right now, it's now in the second position. Then there is Zero, Old Flacucho, which is below Old Flacucho, and then there is Karma and Zero. So yeah, seems like the rounds are still running, and we'll put some music to continue watching the competition. Have fun. So we get the first winners. We have Amphibia, we have Ricardo APL, and then we have Zeta in the second position, because Amphibia and Ricardo seems like they got a shared first position. So I will say that we'll have another round. Let's run the competition again and see who wins. So take a look who is moving around, which positions are changing, and how the bots are competing within them. these are the results for the second round of R2Rs. We ran the same game with the same bots, and we have first position for Amphibia, which is an ARM32 bot. The second position goes for Flacucho, and then the third position is Zeta. Seems like Ricardo got a worse position, which is the fourth one, and yeah, seems like the three first bots are written for ARM32. That's pretty interesting. We'll have more rounds tomorrow, but this is the last one for today. So let's go into the wait scene, and let's go. And then after that, we'll have Pancake speaking about non-mainstream architectures. So, welcome back. This is Pancake. I'm gonna speak about non-mainstream architectures, or basically how politics and economics ruin the computation diversity for the masses. This presentation is gonna be explaining and showing different interesting features that different architectures are providing. But they are basically experiments or something that is not really well known by many people. So get ready for having a quick introduction to history and also to understand and learn new stuff for different CPUs. So if you ask anyone about which is or how many CPUs they know, they will probably say there is Intel, there is ARM, and if you keep asking around, you will probably get some answers about MIPS, PowerPC, and maybe you will even get ReAsm or AVR and PowerPC and so on. But I mean, there are so many more architectures out there, and it's cool to learn a little bit about history of computing and trying to go back in time and trying to understand the beginning, the reasons for all the decisions that have been made in the past. Is also pretty cool and also brings back some interesting things because many old experiments are coming back. So recently we will see that some technologies that have been developed 50 years ago, they are coming back and they are going to be used in future. So let's go into this wall. Let's try to understand what's the situation of all these architectures nowadays, and also we will see how R2 fits in all this environment. How can we use R2 inside all these ancient machines, or how can we use R2 for analyzing the binaries or the system that is there? Because in many cases we don't have the source code, so doing this kind of explorations is really interesting. So first of all, we'll see a quick introduction about the first generation computers that was built on top of vacuum tubes. That was the IBM 650, and that was considered the first generation computers. Then there was the second generation. As you can see, there is IBM all the way. Second generation was made up to transistors. They were much smaller than vacuum tubes, and they were much more power efficient. But 10 years after that, we will see that integrated circuits, which is the beginning of introduction of the silicon technology, managed to get much more powerful machines. And then we go into the fourth generation, which started in the 70s. And this goes for the VLSI, which is very large-scale integrated circuits, which is the PC era. We know that all the general purpose computers that we know nowadays started in the 70s, 80s. And actually most of the most important computers appeared at the time. Then after the VLC era came the fifth generation, which is basically when Intel and AMD joined the game. And they used, or they are known as ULSI, which is ultra large scale integration. So what's next? What's the next generation of computers? Some people say that it's quantum computing that will go after that. Some people say that they will basically switch to one main CPU and different side computing units, like it's happening nowadays for running like artificial intelligence networks and neural networks and other side processing things. And actually this kind of model was designed by Amiga. Amiga computers was being designed to delegate the responsibility of doing some heavy computing operations like voice recognition or stuff like that in separate CPUs, that they were basically delegating the logic, or separate boards that were running a separate computer in there. Also, there is some people that will say ternary will be the next computing generation. And also there is the arsenic thing, which is a gas that is actually much more efficient than silicon. But yeah, don't get into details, and let's continue in that. So there are like different types of computers. The most well-known are the general purpose computer, which is basically any PC or Mac or any phone right nowadays can be considered a general purpose computer. They are self-contained and they focus on the user experience. So basically you have a screen, you have a keyboard, you have a way to interact with that, you can load software in there, you can run programs. So they are used to cover any kind of application that you can imagine. But for some specific applications, you won't be able to use these computers because, I mean, even if you are able to do that, the performance won't be as good as it will be in other architectures, like maybe for supercomputers or mainframes. This is where supercomputers appear. They are designed for solving scientific computations, and they try to abuse the parallelism and vectorization of processes as much as possible. The problem with supercomputers is that they focus on math operations. This means that they won't be interesting for processing large data sets. Like, for example, if you want to process a lot of data from external sources, you will, these machines are not designed to have like a they need to work on a small data set and then process that and then bring back the results. Then there are the mainframes, which are mainly led by IBM. And the mainframes are computers that are designed to work stable. They basically didn't change too much for so many years. But the system is evolving. There is ways for updating and maintaining everything without rebooting the machine. You can basically remove some hard drive without shutting down the machine. You can remove CPUs. You can change whatever you like. Actually, the whole system can be hooked by ASM routines, and you can basically do whatever you like. And these kind of machines are designed to work with large data sets, and they were designed to work with big infrastructures like maybe hospitals or governments and stuff like that, that they need to work 24/7 and they don't need to be affected by temperature changes and things like that. Yeah, we'll speak about mainframes later. And then there is the high performance computing machines, which are designed for computing a lot of data, and we can say that these kind of machines can be like the mix between supercomputers and mainframes, because they are using the vector and parallel processing design, but they are also using different and fast data retrieval. And we can say that Cray was the first HPC, can be also considered a supercomputer. And nowadays the most high performance computing machine is IBM Power 9, which is a PowerPC CPU. The sentence below, I took that from Mare Nostrum, which is the supercomputing center that is located in Barcelona. And they basically replaced the previous supercomputer they were running there, what was Mare Nostrum 3, which was and they basically replaced the whole thing with only 3 racks of Power 9, and they were basically 50% faster. So yeah, it seems like supercomputers are evolving pretty fast, and there is a lot of interesting things to cover in these aspects. But let's begin on the 70s. The 70s was the glorious days of computing. There was nothing written in stone, so basically as long as there was no end users playing or using these kind of machines, everything was ready for experimentation. There was no standards. Actually, not even the binary representation was decided. So there was computers running on ternary operations. Also, not endian was standard. Nowadays, we can say that little endian is the host endian for most any architecture there. And big endian is the network endian, because it's the endian nest that is used for all the network protocols and routers and this kind of hardware that runs the network. But at the time it was not even clear if big endian or little endian or even middle endian was supposed to be used for everything, or which one was supposed to be more performant. So there was a lot of architectures playing with that. Also, there was like different inputs and slow data sources. We can say that, for example, Cray was loading the data from magnetic tapes, and IBM was basically processing all this input and loading programs using punch cards. Punch hole cards are basically paper or plastic cards that are have some holes in there, and the data, the binary, the bits are set in there. Actually, we'll explain more details about the punch card, how they work, after some slides. And also in the 70s, there is the best disco music. So all these technologies were developed basically to fight in the Cold War between US and USSR. There was lots of investigation and lots of interesting experiments, and you can find a lot of documentation, papers, and so on the internet nowadays. So Russia was basically building the Saturn 70. This was a very interesting computer. It was developed before the 60s, and they built about 50 of these machines. And it was the first one was developed in the Moscow State University, and there was basically a team led by Nikolai Rusentov, and there was a theory that instead of depending on zeros and ones, a computer based on a ternary representation, so this means that 0, 1, and 2, it will be much more powerful. And the thing is that electrically, you can represent much easier negative electricity flow, no electricity flow, and positive electricity flow much easily than 0, 1, 2. The thing is that 0, 1, 2 means that will be 0, no electricity, 1, another like maybe 2 volts, and 2 will be represented by 5 volts, for example. The problem of this is that representing that using the different voltages, positive voltages, is much more complicated, and also it brings a lot of problems when trying to detect which is the range that defines if it's 0, 1, or 2. This is the reason why in US all the computers were developed using binary representations. So it was pretty clear to represent which is the range of electricity values that were considered as 0 or the ones that were considered 1. And actually there is a lot of checks to evaluate and reduce the noise and errors that happen with electricity in these machines. The thing is that Nikolai experimented with the balanced ternary representation, which means that you have like a negative electricity for representing minus, then there is 0, and then there is plus. The good part of that is that it's saving a lot of energy, and also it reduces a lot the need for more boundaries. So actually, there is some papers around. You will probably Google for them after the presentation, because I find it really interesting, and I think that if you are into math, you will probably love to learn more about that. But basically, it was explaining and showing how to do divisions, multiplications, and many other math operations based on ternary representations. This is much more performant than in binary, and also it's more memory efficient, because if you can store 3 values for each bit or trait, you can store more data in less space. So it was technologically much more advanced, but the problem is that, well, the Russian government decided that this was not the way to go, because if they wanted to compete with US, they should be basically ripping off the same technologies or trying to compete in the same area. So yeah, I mean, as long as this was abandoned, the whole project was dead. But the thing is that, and they started to develop like binary machines after that. But the thing is that ternary machines were cheaper to develop, also much more performant, or at least that's all the details that you can find in internet nowadays. The thing is that if you Google a little bit more, you will find there is some people developing custom ternary computers. This means that you basically need to develop new software, new mathematics, new compilers, new everything for this kind of hardware. But 2 years ago, a team from Samsung started to develop a ternary computer. They're focusing on developing that for IoT, and you will find some details in the links below. The thing is that R2 is also supporting ternary representations, and if you didn't look into that, you can see this by using the question mark T or the question mark. Well, you can press any number. For example, the question mark with a number, you will see all the different representations for that, and the last one is the ternary. So this is the ternary representation. We can say that 2 will be -1 on the balanced ternary representation, but representing that with a minus, it will be like different. I'm evaluating actually in showing like balanced ternary representations in there, because it wouldn't be much different just using plus, minus, and O sign, just changing the syntax. But you can see that you can take any integer decimal number and get the ternary representation, and actually you can do the same in the other way. So if you use 0t and then we use 1, 2, 0, 1, 1, we'll get that the ternary representation is the correct one, and we have a conversion for that. So if you want to play with ternary representation, you see that these are the tools for in R2 for experimenting with that. So I will say that if we need to support that in CIL, we will probably need to mess with that, because actual computers are processing data in binary. So we can just convert that and then go back to the ternary representation to continue execution. Actually, you can do the same with RAX. And let's go for Cry. Cry is one of my favorite computers when I was a child. I was having, I have lots of memories about this, because it was appearing in different movies, and it was like probably the most powerful computer there, and was impossible to use it or impossible to access to one shell in there. But cool thing is that nowadays things have changed. People is building Cry machines in their home. They basically run. There is a simulator that is able to run the whole operating system, and they are running this in Raspberry Pis and building the thing with printed 3D printed machines. So yeah, the thing is that in the 60s, Cry developed an 80 megahertz CPU. That supported vector processing, and it was running on 64-bit registers. It was also able to handle 32 megabytes of memory, and was loading the data from tapes instead of punch cards, which was much faster. But the thing is that this machine was not. It was really big. It was kind of. You can see the image in the corner of the slides, and these machines were supposed to be used from a host computer. I mean, they were attached to a box or a SAN host, and they were basically compiling the software in the box or SAN machines used on Unix operating systems, and they were pushing the binaries to the COS, which is the Cry operating system that was running in there. Some years after that, Cry implemented the UniCOS operating system, which is a pretty nice Unix operating system that was running natively on Cry. Actually, Cry, as I said before, it was a general purpose computer. So if you open the Cry modularcircuits.com webpage, you will see that there is a link that basically opens a window that SSH into an emulator that is running UniCOS online. So you can get a shell in there, you can execute commands, you can compile in Fortran assembly, because there is like CAS, which is the Cry assembly language, CAL, sorry. And then there is like also a Fortran compiler for it. The thing is that Cry developed a lot of technologies and a lot of compiler optimizations for this CPU, and they were able to detect a lot of cases that it was possible to optimize the algorithms for these kind of things. The thing is that some years later, Cry stopped competing in the scene because there was other players that were basically joining the computer scene. So there was other computers like general purpose computers that was much cheaper, and the difference in computing power was not that different. But if you try to get access to any of this hardware or any of this software, you will find there is like a very passionate community around the world trying to get access to all the documentation, all the tapes and so on. So yeah, I mean, some years later in 2000, Cry developed the T3D machine, which was basically a computer that was running 248 CPUs, and they were combined into a mesh. So basically, you can see that the 3D name in here. It's because the CPUs were located in a 3D area. This means that each CPU had a direct link communication to 6 other CPUs in the same mesh network. The reason for that is because the most slow point when you are doing distributed computing is the communication channel. Most distributed computers are basically using one channel. There is a bus that is sending data encoded with some headers, and other processors will be taking the data chunks from this bus when they are seeing that this data belongs to them. The problem is that if you try to multiplex a single bus between a lot of CPUs, you will see that this doesn't work because at the end there's a huge bottleneck in there. So the original solution from Cry was to basically create a mesh of CPUs that they were interconnected between them. And you basically delegate the responsibility of who is starting the next CPU and sending the data to the other CPUs, like if it was a neural network. And that was pretty cool, and the compilers were taking advantage of these kind of models. The thing is that despite getting some sales with all of that, it was too much complex technology for using by many scientific people, so they were picking different solutions for that. So the company started having losing money, and yeah. So also another interesting finding is that they were starting to use gallium arsenide technology instead of silicon. The thing is that the gallium arsenide combination of gases creates a semiconductor which is much more powerful, and it doesn't heat as the silicon. And well, if you Google a little bit about that, you will see that there is some papers from last year saying that there is basically a bunch of investors that are getting advantage into this technology and trying to get that to work for about in 5-10 years. We'll see some CPUs running on gallium arsenide probably. So yeah, things from the past that are appearing coming back in the future. So yeah, there is some little story about Cry and the Cold War, so you can read the reasons or the explanations or the use cases for Cry and how it was used for developing and analyzing different environments or technological solutions. So let's speak about the assembly. So basically, if you SSH into this machine, or you start the Cry emulator, because there is an open source Cry emulator there. It's written in C++. That's the reason why the disassembly is not implemented in R2 yet, but will be shipped in R2PM, and probably I will end up writing an assembler, disassembler for R2 natively. So if you look into the assembly code, it looks like pseudocode. So you have like the operand, and actually this is not I mean, there are like different representations for the Cry assembly, and some of these are using the equals and some of them are not. So this means that in this case we are representing a move operation, but this move operation is using OR on the value of A. The thing is that this equal sign is depending on the left element of the pair, and this left element is a register. If the left element is an operation, it will be behaving differently. And the binary representation, it's not like fixed instruction set, so you can have instructions for 2 bytes or 4 bytes. I think that there is also instructions of 6 bytes. But it was working on 64-bit values. And also there was vector operations. It was possible to make like MMX or SSE instructions in this architecture. So Cry running Unique OS, it was able to run C programs, not just C programs, but also compiler inside. It was also able to run Fortran. It comes with C shell, but it's also able to run Bash and other tools like Beam, for example. And yeah, I tried to build R2, but yeah, there is no way to build R2 in that system, mainly because that was before the 90s. This means that the C accepted for this machine, or this compiler toolchains, it's not even C90. So it's C89, and there is some rules that I'm following compile the code using this toolchain. But I managed to build R0. R0 is the a small hexadecimal disassembler editor for the command line, kind of like the child of R2. And well, it builds and you can run it there. And I will show you. I will show some screenshots later. This is in the right side. You will see that this is the shell that you get when you log into the Unicode system. And yeah, as I said, it's very nice. You have like this shell, it says Unix single user, but you basically have like a /dev. You can have a /proc. Only for procs, there is no metadata in there or details from the hardware. You have like different levels of users. Yeah, it was a full Unix operating system, and it was pretty modern for the time. So let's speak about the machines that were used for controlling the Cry. The Cry supercomputer were managed mainly by machines built by DEC, the DEC company, or used by Sun Microsystems. So they had software. There were RISC computers. This means a reduced instruction set, and they were all pretty advanced at the time. So let's speak about the PDP-11. The PDP-11 was famous because it was used for landing in the moon. Yeah, I mean, there is all the source for all this software online. It was open sourced a while ago, I think a couple of years, 3 years ago. So you can Google for that and download all that stuff around. It's very interesting. Then there is, well, PDP-11 was a 16-bit machine, but then they developed BAX. BAX is a 32-bit machine. And this 32-bit machine is able to run at BSD. There are many other Unix systems that are running in BAX, but I managed to run NetBSD because it was pretty simple. It was just downloading the image and running the BAX emulator. The BAX emulator is open source, and it was written by one of the bosses in DEC. It was one of the engineers that was basically building the company, and everything is open source, still maintained. It's in GitHub, and it's called SIMH, SIMH. And this emulator is able to run all the PDP machines as well as all the BAX machines. So yeah, you can run NetBSD, you can build C programs with there. And the cool thing is that you can even build R2. So you can run R2 in BAX. Then there is Alpha, which was developed in the 90s, and it was the 64-bit machine, a general purpose machine that was running even on 1 gigahertz. It was possible to run Windows NT, but it was mainly used for running Unix systems in there. Yeah, I mean, all the three architectures are supported by R2, so you can load any binary from these three machines below inside R2, and you will be able to disassemble and get some analysis for these binaries. The thing is that the file formats were different. They were not using ELF, and you will need probably to implement some more stuff, and the analysis is quite not complete right now. But yeah, I mean, if you want to have a look at any of these machines, I will tell you that R2 will be the first step for checking out. So let's see how the BAX works. They use like 66 byte length instructions. This doesn't mean that all the instructions are that big, but the largest instruction is that size, so that's pretty huge. So it's a variable instruction set, so you can have like small instructions or large ones. You can see the disassembly at the right side. This is from object-dump, but you can also take that from R2, which is using the same disassembler of binoodles. This was a 32-bit CPU and contained 16 registers, and there was like 4,000 byte vector registers for vector operations. Also, there was several PDP models were using 6, 8, 12, or 18 bits. So as I said before, not even the 16 or 32-bit naming was that standard at the time. So there was like so many different bit sizes in the instruction sets, as well in the register sizes. This machine had 4 different privilege levels, so you can have like a kernel side, a supervisor, user and root, for example. And it was pretty fast. It was as fast as the S360, which was the CPU developed by IBM for the mainframes. And there was a mode for running PDP-11 software, so it was that was the reason why it was so popular at the time. So let's see how to run R2 and NetBSD on the Bug Simulator. You can just install the brew install sim8. You can just download the source or download the binaries from the website. It's very portable and it's really fast, but yeah, it depends on the kind of things that you're going to run there. But the code is pretty nice to read. This is the list of all the hardware, and in the right side you will see that you need to execute the bugs tool. The bugs program is the emulator for bugs, and you pass the configuration option to specify which is the size for the memory, which is where is each of the disk and the ISO image, etc., and then the network interface. Then you say that you want to boot the CPU, and then you boot from the image that is loaded into memory. And that's it. This way you can just run NetBSD on bugs, and then you can compile R2 inside. Let's speak about middle endian, because there is like the legend that some CPUs were using middle endian at the time, but that's not completely true. I mean, there was little endian machines, big endian machines, but PDP-11, for example, or bugs, they implemented support for some extended instructions that were not supposed to be in the initial CPU models. And these instructions were mainly messing with floating point data. They were using middle endian instructions. R2 provides a way to get the data from any endian using the PBE command. The PBE command basically expresses the order of the bytes. So for example, 4, 3, 2, 1, that will be a big endian, little endian. Big endian. 1, 2, 3, 4, which is the big endian, and then you go for middle endian, which could be 1, 3, 2, 4, or 1, 2, 3, 2, or whatever, any order you can imagine for the endian. So yeah, there is a large option for there. The thing is that there is no need for implementing more than 2 endianness in a disassembler. Only for processing data when you are going to be emulating the instructions or retrieving the data from that memory. Let's speak about mainframes. I will go back about the cyclic memory later. So at the same time that all that was happening, IBM was trying to fight a different competition. They were basically focusing on mainframes, and they were just working on systems that were pretty stable, and they were not supposed to be shut down at any time. The thing is that if you try to shut down an emulator for MBS and you don't do it properly, you end up probably having like corrupted data. I don't know if this is still happening. I probably not. and although we basically have like the more critical part running on separate operating systems and machines, so they need they're pretty difficult to get them shut down. So 360, which is the grandfather of DOS 360, which is all the operating system that we're running on this 360 CPUs. R2 provides the disassembler analysis plugins for these two architectures, but there is also different CPU models for them. And yeah, I mean, there is like some incompatibilities for the instruction sets, and you will see that that's the reason why we are not able to run like new Linux distributions on them or things like that, because the instruction sets are different. But let's explain some curiosities about IBM and MBS. First of all, you know why there is a standard of 80 for 25 in the screen terminals on IBM PCs? I mean, this was populated on the IB PCs because Unix systems were having like different resolutions for the screen. But all the IBM PCs were using that. And the reason for this is because this is all the data you can fit in a single punch card. So you have like 80 columns and 25 rows, and you store all the data inside this paper using this format. The thing is that you can see that the text in this punch card is not following the ASCII standard. We can see some example encoding for text that was not the ASCII one. And as long as there was no standard for anything, they basically implemented their own, which is the ABCDIC. And this standard was designed to be written in punch. Try to print ASCII on a punch card, you will probably get broken paper because you have so many holes that are next one after the other one. So ABCDIC was designed to be distributing the amount of holes in the paper in a way that it was making the paper more resistant. Yeah, I mean, there is so many interesting details on that I wouldn't go. So basically in this all that stuff. So basically it was possible to locate more memory than the one that was able in the RAM. So you can basically access the memory, so the hard drive, for example, or magnetic tape, but the program itself was accessing the memory. So this was reducing the amount of fragmentation in this memory. It was also simplifying a lot the access of the security, because it was possible to isolate each process in a separate memory space. And as long as all the programs was having like a physically separated amount of memory or disk, it was much safer and faster because there was no layers in the middle that was routing all the bytes for accessing these resources. The thing is that as long as they basically care about retrocompatibility, because companies won't be rewriting the software when there is a new machine in there, they will basically keeping support for all the original languages like COBOL, Fortran, and C, for example. But there is also Rex, which is one of the scripting languages that was born in these machines, and it was still used, and it's a language that is available in any operating system you can imagine. So there are acronyms and that you will probably need to Google a couple of times in order to understand what's going on. Yeah, so IBM loves this kind of conventions. So how can we run R2 in MBS? Okay, so first of all we need to say that Z architecture, which is the last, so the last releases of the last models of the MBS 390 CPUs, is able to virtualize other operating systems inside. So you can basically have Linux running on below a ZOS, and this is probably the way that most system administrators are using these kind of machines nowadays, because using MBS for critical things is ideal, but there is very little people that is able to understand and develop for these machines. MBS doesn't have much memory, so each process has a very limited amount of memory, and actually when you try to run anything in there you have to provide a script, and this script defines how to execute that script. This means that when you execute a program you have to define which is the input, which is the output, where the data will be stored, which is what the program will be doing, and many other details like memory layout, this layout, and many other stuff that is kind of annoying because it's, I mean, you don't work on a shell, you work on a graphical environment, which is a text environment, and you define these kind of instructions that you queue into the system. So the thing is, when you run a program in a mainframe, you basically define a set of steps that the application should be doing, and you start the task, and then the task runs in background. You don't know what's going on. Then after that, you get the result when the job is done, and you can get the results. So the thing is that, okay, there is like an hexadecimal editor already, there is a disassembler already. Actually, the standard way for shipping software in this kind of machines is by providing the assembly source code. So all the compilers that target these systems are providing an assembly plain text output, and you basically feed this plain text output into the console through a serial port, and this assembler code is assembled by the machine and then compiled into binary that is executed in memory. So it's not that easy to get binary from any program that is shipped in these machines. Also, we don't supposed to happen in background, so we don't have interaction with them. So what can we do? Okay, so I have different ideas for tracking this problem. I'm basically experimenting with the TK4 emulator, which is a distro for MBS. I'll explain and show that later. But basically, you can get C programs running there. So one way to access that will be one option will be to use R2 Frida to hook into the emulator to get access into all the functions that are accessing the CPU and the memory. So you can implement the debugger on top of that, so you can modify this. I will show how to do that in a Game Boy tomorrow. But this is kind of like not a real use case, because in real hardware you cannot do that. So the way to do that, we can also implement R2 pipe. We can have a wrap server that is running in a job in background, and then we can connect to it through TCP IP, for example, or serial. That will be another option. And also ways to integrate R2 in there will be to get R0 running indirectly in there, because we can implement an ISPF interface to R0 and get that running inside the MBS interface. And yeah, I mean, there is already disassembler and hexadecimal editor, as I said before, but it's not that easy to find it, and having like overruns overrunning in these systems, it's actually pretty interesting. So yeah, this is all the options that we have right now, and hopefully I will be pushing some updates from time to time in this interesting project. So let's speak about REX. I implemented R2 pipe support for REX. R2 pipe, as you probably know, is a way to instrument R2 using any programming language that you pass the command that you want to run, you get the output. So REX looks like the thing in the right. So yeah, I mean, it's it's kind of like a shell script, something like that, but it's more powerful. You have different types of variables. You have methods, which are procedures. You have local and global variables, etc. So there is like, the syntax is not that difficult. So it was possible to implement the logic for running this. The thing is that I'm using Regina, which is the GNU implementation of REX, the scripting language. You can run REX, as I said, in Amiga. It was also the standard scripting language for OS2. And it's available in MS2-DOS as well as many other old operating systems, but it's also able to run on Linux, Mac, Windows, whatever. The thing is that there are some details that are different, basically the functions or the APIs that you can use. And actually, when you try to run REX on MBS, you have like different extensions that you need to sign or you need to approve or get approved by IBM to run there. This kind of thing. So any interesting thing will be like reading, writing memory, accessing files, and things like that is not something that you will be easily doing from an MBS shell, from running a REX script. Okay, so let's go into the CPU. These mainframe machines uses S3 something CPUs. You can see that by using the R2, you can pick any of the two disassemblers. As you see, there is a GNU one, and the other one is based on Capstone. Both disassemblers are pretty well working, but the thing is that depending on the machine that you are trying to disassemble, you will need to trick the ASM.CPU variable. Otherwise, you will get like trash of disassembly. You can see that in the disassembly in the right. So this is a hello world. It was compiled in MBS. You can see that there is some text alone. So that what you see in the left side is basically the assembly code that was generated by the C compiler. And the problem of C compilers in these systems is that as long as I said before, the tasks or the jobs have a very little memory, you don't have a way to compile big C programs. You can only compile small C programs. So usually the way to ship programs in these machines is compiling it outside, go directly into the MBS system. So there is an open source compiler that I don't think you will be able to display in text. So you see, this is the standard syntax for IBM for loading assembly code. The thing is that if you get binary generated by this assembly code, you can disassemble the program using R2. You can compare these assemblies that are actually the same, and all the invalidated and assigned instructions are data that is embedded inside the code. Okay, so let's speak about TK4. TK4 is also known as turnkey for a system. There is a cat sleeping in the loading image, and it's basically a distro of MBS 3.8J, which was the version that, well, the US government paid a little bit to IBM to get some improvements in this operating system, so they were forced to open source, or not open source, but publish some images and make that public domain. So, and this is actually the only legal way for using an MBS system, unless if you pay to IBM the cost of having like all these machines and all the software. So there is adding new software, improving the configurations, adding new compilers and things like that. But there is some pain in the system still. So for example, if you shut down the VM quickly, you will basically get like corrupted images, and you will probably need to lose all the stuff that you have previously done. It's only possible to run very old Debian Linux systems. The reason for that is because there is a lag for many instructions that are not even documented. So it was not possible to run these kind of things in there, but it's possible to run Linux in this system, so it's also possible to compile R2. And that's something I plan to do before the end of the year. And I will be showing some screenshots when I get it. Also, getting TCP/IP running in these systems is very difficult. Another fun thing is that all the passwords are case insensitive, so it doesn't matter if you type the password in lowercase or uppercase. So yeah, I mean, you have like multiple users, but it doesn't care if it's lowercase or uppercase. And the four main languages that you can use in there are Fortran, Rex, Assembly, and C. So let's go back and speak about the char sets that were defined by IBM. So R2 have support for char sets, so you can change the cfg.charset config variable, as you can see in the screenshot or in the test case below, and it will be printing the data when you use px or ps for printing a string or printing hexadecimal. And as you see, C8 doesn't stand for H in ASCII. Okay, so the only actual character that is ASCII is the 40, which is the @ sign, and the @ sign in SBCDEC is the lowercase m. No, sorry, lower dash. So yeah, you see. So there is support for different char sets. You can see them that the question mark at the end of instead of the value. And the thing is that if you try to log into any old Unix system, you will see that XXD is available there, and there is a flag that has been there from time to time, which is the uppercase A, and this flag and other flags are all able to convert from ASCII to ABCDIC. So yeah, you can use XD for throwing binaries or text files from different mainframes machines. If you want to learn more about that, I will recommend you to watch the videos from Moshix, join the Discord server. There is like a large community of mainframe fanboys in there. You may install the TK4 system, and yeah, this system is running on Hercules, which is has been replaced by Hyperion, which is the new emulator that is able to run the S3 80, I think, not 90, and load all the images for this operating system. So let's speak about other architectures. I will be explaining some quick topics on them, mainly for jumping from one to the other one to get more interesting details on them. So let's speak about Amiga, because it was a very successful computer at the time, and there is still a lot of people using it. It was initially running on Motorola CPU, but at the end of the company they end up like building PowerPC machines and running that on Warp OS, which was the name of the new operating system. Workbench was the original one for running in Amiga. Actually, there is people building boards that were attached to the Amiga motherboard, that they were running like different CPUs or architectures. Like you can plug an Intel CPU in an Amiga, and you can run Doom or Quake in that CPU, and then you can basically get the output of the video for that into the Amiga, so you can play actual games in Amiga by just attaching new hardware to it. And this was possible by the design, because the design of Amiga was supposed to be it was designed by a dog. I don't know if you know the story, but the thing is that maybe it's a legend, but the legend says that the Amiga CPU and motherboard was designed in a garage, and they had a dog, and when this dog was sleeping or making their needs, they were basically messing the floor. So they put all the CPU and motherboard design in the floor, and when the dog was shitting in one of the places, it was meaning that this place was wrongly designed. So they basically decided to let the dog decide which was wrong and which was good. Yeah, R2 supports the Motorola CPU. You can also load home binaries in it. So yeah, it's if you want to have a look at and contribute to the amazing Amiga community, because there is still a lot of people doing things and writing software for it, and also making music, writing video games, demo scene, and so on. You can also use R2 for analyzing that. There is also some interesting computers that are named fantasy computers. These fantasy computers started with the Pico 8 machine. This machine is not real, it's a fantasy computer, as I said like a couple of times. And the Pico 8 was basically a CPU that is not a CPU. It's basically a machine that provides some hardware specifications, but the way to interact with the hardware is done by scripting languages. This means Lua, for example, or JavaScript. The thing is that it was very nice to develop in this kind of hardware, because at the end you create like old hardware like the Amiga one and so on. So you have access to the color palette, you have direct access to the screen, to the key control, and all the stuff that you need. And you have like very simple operations to work on this data. So you can create retro games using retro techniques, like doing animations by swapping color palettes and things like that in all these simulators. But Pico 8 was developed. At the beginning, it's a commercial product, and you can run it in many mobile phones or web pages or game consoles and so on. But there is so many other fantasy computers. You can see that there is B8, there is Basic 8, Lambda 8, Lico 12, Retro 40, and TIC 80. If you have been participating in the CTF, you will see that there is one of the proofs that was written for TIC 80, and it was written in JavaScript. So yeah, at the end it's like a package that is supported, so it's a file format that's supported by R2, so you can get all the sections. So you get the code section, the data section, the sprites, music. You can load the TIC 80 tiny computer, you have like a shell, and you can list all the images. So for example, if you load the demo that I wrote, which was, I think it was in the JavaScript side. Yeah, I messed with that, but okay, so I can run this thing. Oh, it's also another failing test. I will just load the hello world thing. Okay, so we can also get into the editor, so we can basically change the code for this program. We have a sprite editor, there is also a map editor, music editor, tracker music. So everything is integrated into the same environment, so you can make animations, create videos, record the code. You can also develop in full editors, not just in here, because you have like copy paste. You can search for stuff. There is like a method for methods, and you can basically run this anywhere. So what the format that these fantasy computers work is basically packing all the data in sections, and the code section is basically just zipping the contents of the script. So it can be Lua, can be JavaScript, and the way to define which language is being used is in the headers of the. So basically, the first line of the script in a comment they define if it's Lua, JavaScript, or whatever it is. Okay, so let's speak about memory for the Game Boy. One of the main interests of Conrad in R2 was to basically get all the features that were available in the Game Boy hardware to be available in R2. So one of the main problematic ones is the I/O banks. So the I/O banks is a way to extend the memory for the Game Boy. So when the game was bigger than the memory bus, you need to swap this memory with another content, and I/O banks permitted to do that. So the thing is that you have like 4 banks that you can be swapping at any time, and the emulation for that basically requires taking care of this. So when you are swapping the memory, you have to assume that the data will be different, and actually there was no way to do that until now. Now R2 implements memory banks, so you can define different memory layouts with different maps. So you basically have a default memory bank which contains all the current maps, but then you can create another memory bank and create like different layout. This can be also useful for emulating segmented memory. You can have like different memory banks swapping and selecting different regions depending on the value of the segment register, but can be also useful for emulating kernel because the kernel have like a different memory model than the applications. So when you are swapping context, you basically get the different memory bank enabled. So yeah, you can use the OMB command. Let me show you how to do that. So we use OM, we have only one map, which is, because I'm loading the malloc with half kilobyte there. And we can use the OMB, which provides the default memory, like specify the ID for the bank that we want to switch to. We can create a new one with a given name, and then we can add and delete maps to this, to the memory bank, like this. And then just using OMB and ID, we will be swapping to one or the other one. Okay, let's speak about P850. This is an architecture that is widely used in automotive industry, basically for cars and so on, but it's also important for real-time critical systems. This CPU is designed to work on different and large ranges of temperature, so this means that it should be always stable, independently if it's hot or really cold outside. And in order to do that, it provides a different optimizations and technologies, like for example the parallel sync execution. This means that some B850 models will be having two cores executing the same code, and basically comparing the values of everything inside the CPU. And in case that any of these two parallel executions differs, then we'll be stopping that. Because it will be considering that there is an error, and then we'll be executing the same instructions again until the both CPUs are doing good. There is also cyclic memory. The reason for cyclic memory, which is something is very interesting, and no tool out there is available to handle that except R2. R2 is supports cyclic memory. Is that compilers can do some fun optimizations. By fun optimizations, I mean that the memory can be only executed in the first cycle of the memory. So, for example, if you have like a 32-bit map, but memory model, but you can only access 26 bits. This means that it will be cycling when you are accessing higher addresses. So if you do a memory dump on this, and you try to access a higher memory address than the one that was supposed to be accessing by the memory bus, the address bus, you will basically get the same memory once over and over and over. The thing is that this CPU is using memory mapped devices, so the higher addresses, the ones that are starting with FFFF, are usually containing mapped devices, and in the lower ones you have like usually vector, interrupter handlers, and so on. So the thing is that if you want an interrupt handler to access these higher addresses, you just need to make a relative reference in a negative way. So you basically create like a negative reference from the beginning of the CPU of the memory address space, this in a higher memory address. So it's a cyclic thing. One of the problems or one of the characteristics of the cyclic model is that only the first page will be executable. So you cannot jump below the address 0, or you cannot jump above the higher of this. So yeah, you can define the cyclic memory model with R2, and all the flags and all the data will be and the code will be mapped properly. Actually, only the first one will be able to click. Also, there is one instruction that is pretty interesting that is only in the E2 models. This instruction is switch, and the switch instruction is implementing a jump table. This helps a lot on implementing help for the compiler. So basically it provides a way to say that you know that there is an index, an array of destinations, and you know that there is the pointer that defines which is the destination you want to go. R2 implemented support for jump table analysis using a seal. So basically emulating with a seal the code that is before the switch instruction, we can determine which are the boundaries and the ranges for and the destinations for B80. You will see that there is 3 disassemblers for it. The first one is quite old, but you probably may still find some hardware using it. The B850 is only supporting the very first model. This means that you won't be finding the switch instruction, and there is some instruction that has changed the binary representation. And the GNU1 is supporting more models. So you can pick, for example, if you go into the asm.arch b850.gnu, you can pick all the submodels. So you can basically GNU is the standard toolchain for building for these machines. You can have like a GCC for compiling programs for this architecture. So all the disassemblers are in sync with the manufacturer, or at least I hope that so. So you can find that there is like A2 and E2 V3 and also A3 V5 models. But also not just these 3 disassemblers are shipped in R2, but also there is support in R2 Ghidra. How to do that? If you use R2 Ghidra as a disassembler, you can see that there is a CPU that can be used to define which is the model that you want the architecture that you want to select from the R2 Ghidra, the compilers and disassemblers. So all these architectures are implemented in Slate. So all that stuff is basically Slate. Okay, so let's pick ASM.CPU, B850, okay. So it seems to work. Let's open binary and let's try to disassemble that. Okay, so it seems like this assembly looks good, but all the instructions look like invalid. So this is why they are painted in red. So this is because we didn't select the architecture for the AL plugin. And when we pick the NL.CPU model, we basically get all the analysis and disassembly in sync. So this will be the disassembly for a bunch of instructions for the 850 program. And the cool thing is that you can have like a seal. So for example, this first instruction provides there's a pseudo. Oh, it's not still working now. Let me try to initialize that and then the p85. Oops, forgot to. Okay, now we have proper analysis with all the jump lines. We can analyze this and get the graph. So all this assembly looks correct. And let's go for the seal. You see that there is the seal expression in there. All these seal expressions are generated from the r2con2021 slate representation. We can enable the ReAsm.seal equals true, and we'll get, instead of the instructions, you will get the seal expressions for that. One of the problems is that slate for B850 is not really complete, and many of these are wrong. So yeah, I fixed a bunch of them, but there are still many that are not working as expected. So you cannot use a seal for emulating any function or any program in this architecture. But it's improving over time. And finally, there is the /ru command for finding UDS can. So if you're analyzing stuff that runs in a car, you probably need to find where the can tables. Okay, so another interesting CPU is the M32. This is a 32-bit microcomputer from ReAsm. This is also from ReAsm. And it's used mainly for medical applications and automation. And it was only supported in IDA, but I added support in R2 through a plugin that is accessible through r2pm. So you can r2pm-ci m32c, and you will get this plugin loaded into R2. The thing is that I was thinking that it was as easy as just taking the code from binutils and just wrapping the few functions inside the plugin to make that work, but it was not that easy. The thing is that I didn't know that, but GNU developed like a CGen program that is stands for CPU generator. That it's kind of a slate, but from GNU. It's basically a language that defines in Lisp what each instruction looks like and how it works, and then it generates all the C code for disassembling, analyzing, and so on. The problem is that this CGen thing works nice for a hello world, but if you try to do something with a real architecture, you will get like some really huge code bases. But huge, I mean that maybe, I mean, there is some architectures in binutils are implemented on this, but for example, you won't be able to get that for Intel. I mean, the M32C plugin is taking about you see, it's kind of big. This is because it's compiled, but I can basically clean the thing, and we will see that's 10 megabytes, and it's just for a disassembler of a microcontroller. So the final code that is generated for that is not ideal, and that's the reason why I'm not shipping this architecture in R2 by default. So actually, there are some alternatives for having like a proper disassembler there, but it's work in progress. So if anyone wants to contribute or improve or implement an M32C disassembler, you can look into the Ishimeo libraries in Rust, or you can implement that from scratch by taking a look at the papers. Also, another interesting feature that is not, this one is not supported in R2, is the register windows. So Spark processors basically implement a way to define a range of registers to be used by the program. These CPUs have a large amount of registers, up to 500 for example, and they basically use the registers as a way to define stack frames. So instead of pushing data into the stack, they shift the registers values. So you have like a window that defines 8 registers for input, 8 registers for output, 8 for global variables. When you shift this window, you basically get access to the previous variables, and you have new registers clean for your own use. This way it's possible to improve the performance, because there is many functions that are calling other functions, and then you don't need to access memory. You just need to access registers. This window is defined by the CWP register, and when you increase that with save or restore, you will basically moving that window. And yeah, this is a feature that is implemented in Spark, and that's an alive architecture. I mean, there is like actual Spark processors nowadays, but this is not implemented in a rec, so it will be cool to have this feature in R2. And that's all for me. This is the end of my presentation and the end of the second day of the conference. Hope you enjoyed it. And if you have any question, or if you're interested in anything of that, I will be uploading and pushing the slides in tomorrow after the conference, so everybody will be able to check all the details if you are interested. So yeah, thanks for watching, and see you tomorrow.